Hi everyone. We will solve some problems that we didn't before solve in the classes in the first 6 worksheets. So let's start. This one is from the first worksheet, the problem 8. It's so easy actually. So we will show this inequality when n is in between 1 and 4. And it's a positive integer. So for n equals to 1, first we compute this one and then this. Here we see 2 is equal to that, so this inequality holds. Now for n equals to 2, we get this result again. So for each case, we have the same inequality. Thus, it is satisfied, the statement satisfied and for any n in this interval. Okay. Now this is from second worksheet. Now we will prove by induction the sum of n positive integers, even integers, is equal to this. Where is the? We will prove this equality. Sorry. We will prove this equality. Okay. Now for n equals to 1, it means if we have only one even integer, which is positive, we have 2 then. Thus the sum is 2. It's the only even integer that we add. So we have 2. When n equals to 2, then it means we have 2 even integers. 2 first positive even integers are 2 and 4. We add them and get 6. Now for n equals to 3, we have this sum. So it seems actually n times, here we have 2 for example, n times n plus 1, which is 3, so we get 6. For example, for this part, we have 3 times 4, we have 12. So you may guess this sum also from the, if you know this, from this. This is equal to, sorry, it's 1. This is equal to this. You can also show this one by yourself. So if you know this, then you may guess when you have only even integers, okay, only even ones, then you will have this 2 times of this summation. So we will prove this. Now, how do we prove? We will prove by induction on n. So base case is for n equals to 1. So if we have only one even integer, which is positive, then we have only 2. Now on the left, we will have only 2. What about on the right side? Now we have n equals to 1, so we plug n equals to 1 here and get this 2. So on the left and the right, we get the same values. So it holds, this statement, this equality holds for the base step. Now we will suppose it is true for n, and we will show for n plus 1. Now how do we do that? So to show this for n plus 1, we plug n equals to n plus 1 there and get this equality. And get this equality, this one. So we need to show this. Now we start from the left, okay? We wrote here the left part. By assumption, what's that? We assumed it's true for n, so we have this, okay? For why do we have 2n here? Because we know they all even integers, that's why we denote it by this, okay? So we assume this, then we know this part is equal to this n times n plus 1, okay? Now we have this also here. Now in the parentheses of n plus 1, we get n plus 1 times n plus 2, which is we wanted to see on the right, okay? So we started from the left and get the right hand side. Okay, so it means it's true for any n. Okay. Now we have again a problem from the second worksheet. Now we will compute the number of the bit strings of length 8. Now for each digit, we have two options, as you see, 0 and 1, remember. So it's called product rule, I guess. So for each case, you have two options and you have 8 many digits. So we have 2 to the 8 bit strings of length 8. Okay. Now this is also from the second worksheet. We will compute the ways such that a photographer at a wedding arrange 6 people, but we have 10 people, okay? We want only 6 of them to be arranged, okay? Now we will, we have the first case. We want this, in this picture, bride should be in it, okay? We want this. Now we have already 10 people. Now, if we don't compute one, the bride, we have 9 many then. So we need to have 6 many people to get that photograph, okay? But we have already bride on some side, okay? So we need to pick 5 many people among these 9 people, okay, to get in total 6 people. Okay, we have bride and remaining people. The number of the remaining people is 5. So we need to choose 5 people among these 9 people. Hence we have this part. Now what's this? We don't only choose the people, but we arrange them. So how do we arrange people for objects and many objects, for example? It's n factorial. So we have 6 factorial there, okay? So we get this result. Okay, now we want both bride and groom to be in the picture. Now we have then 8 many people left, okay, except this bride and groom. Now we have 2 people there. We want 6 of them. So the left is 4. Thus we need to pick 4 people among these 8 ones. Okay, and this is the same. We arrange them. That's why we have 6 factorial. So this is the result. Okay. Now we want exactly one of the bride and the groom is in the picture. Now, exactly one of them we want. So we cannot both bride and groom in the picture. So if we have only bride, for example, then we have how many people left? 9. But we want the groom not to be in that picture, so we have actually 8 people to choose. 5 people to choose among 8 people, okay? So that's why we have this. We multiply it as usual by this factorial, okay? Now, why do we multiply it? Because this was only for the case where the bride in the picture, okay? And for the groom, gender equality, so we need to multiply it by 2. Thus, we have this result. Okay. So this is from third worksheet. So in a ball, we have 10 red balls and 10 blue balls. Okay, somebody will choose these randomly balls without looking at them. So first one, we will find the number to be sure that the person choose or select having at least 3 balls of the same color. Okay. Now, in how many ways or how many selection will be will make her to be sure that at least 3 balls of the same color. Now, if she selects 3 balls, then only 2 of them may be of the same color, because it's not the case, but it's maybe, so it's not for sure. Okay. For example, 2 balls can be red and 1 ball can be blue, so it's not for sure. Now, if she selects 4, then, for example, 2 of them may be red and the remaining ones, which are 2, may be blue, so it's not for sure. But if she selects 5, then there will be at least 3 balls of the same color, because if this is not the case, then we will have these ones. Either we will have too many balls of the same color and 2 other and 1, but this means we have 3 colors. But we know in a ball there are only red and blue balls, so it's not the case. And what about it? It means the 5 balls have different colors, but then it means we have 5 main colors. So again, this is not the case, and also similarly, this is not the case. And this is the only way to have, or this 2 plus 3, it means red, blue, or blue, red. Okay, this is the only way to, you may say, separate the balls with regard according to the color. Okay, so at least 3 of them will be of the same color. Okay. So this one is easier. Now, how many balls must you select to be sure of having at least 3 blue balls? We have 10 red balls. Okay, maybe she selected 10 many times balls, and each time she got red ball, right? This is the life, so it may. Okay, we have 10 then, 10 red balls. But if she continues to select the balls, she will necessarily get blue balls, and we want she to have at least 3 blue balls. She should select 3 balls also, so we get 13. Okay, this is enough to be sure. Now we have, this is pretty good, so I wished I solved before, so sorry about it. This is again from worksheet 3. Now, a computer network consists of 6 computers. Each computer is directly connected to 0 or more of the other computers. Okay, we will prove that there are at least 2 computers which are directly connected to the same number of other computers. So we will use this theorem, which says if you have n objects which are placed into k boxes, then there's at least the same things in the question and in the theorem. There's at least 1 box containing at least this many objects. Here there's a recall for this notation. Okay. Now, what do we do? It's clear that n equals to 6 here, but we have 6 many computers. What about k? Let's consider the cases. If, for example, there's a computer which is not connected with any of the other computers, then this is the case, because we know the connection number is either 0 or more, so it may be. So if we have 0, Then we have these cases. We cannot have 5 because if we have 5, it means there is a computer which is connected with each of the other computers, so there won't be any computer which has no connection. Okay, so this is one case. Here you see we have 5 options, 5 connections. Okay, so and the other one is this, of course. There may be 5 many connections, so but in this case we won't have 0. Okay, so we have the 2 cases, and each case we have 5 many connections. Okay, so we have k equals to 5. Okay, now we apply the theorem. We compute this one. The 6 over 5 is this. So what's the smallest integer greater than 1.2? It's 2. Okay, so it means there's at least 2 bugs. Sorry, not bugs. 2 computers that are directly connected to the same number of other computers. Okay. Now again, third worksheet. So we will compute the number of the bit strings again of length 10, which contain at least 3 ones and at least 3 zeros. We will compute, instead of that, we will compute this one. This is easier. So this is the, you may say, negation of the desired one. So what's the number of bit strings of length 10? It's 2 to the 10. So note that before. Now let's compute this one. Okay, this means the number of this set, the cardinality of this set, the number of the elements of this set. Okay, so what's this? Bit strings containing no one. So each digit has 0. It means there is only one way to create that string. So it's 1. Okay, the number of bit strings containing no ones is 1. And similarly, for this case, we have 1, 2. Okay, now what's the number of bit strings containing only 1, 1? We have 10 many digits, right? The length is 10. We have 10 many digits, and only one we want it to be 1, so only one of them. So we pick only one of these 10 many digits. So we have 10 in total. And for this case, same. Now 2 ones, we choose 2 among 10, so we get this. Okay, and for the case where instead of 1 we have 0, it's the same. Then this is the number of this, the number of the elements of this step is 2 plus 20 plus 90. Okay, for each of them we have 2 times. So this is the number of the elements of this set. So its reverse is this, 2 to the 10 subtract that number. So we get this. Okay. Okay. Now, fourth worksheet, problem 2, we will compute the probability that the sum of the numbers on 2 dice is even when they are rolled. Okay, the sum of the numbers. So we first write the possibilities, not the possibilities, but events. So either we will have 2 odd numbers to get the sum, even sum, or 2 even numbers. So for 1, if we fix the first component as 1, we need to have 1 for the second, or 3 or 5. Okay. And similarly, if we have 2 to get an even sum, for example, 2 plus 2 is 4, so it's even. So we change the second one. Like we cannot have 2, 3. The sum is 5, so we cannot. Okay. So using this idea, we wrote all of them. There is no simpler way to write that. Okay, and how many events we have? We have 18. And what's the total number? For the first one, we have 6 many, and for the second one, we have 6 many numbers. So we have 6 times 6. So we get 1/2. Now, what's the probability that a positive integer not exceeding 100 selected at a random is divisible by 5 or 7? So there are numbers that are divisible by both 7 and 5. So we need to compute these ones. P of A, where P of A is the probability to get uh, a number between 0 and hundreds divisible by 5. So P of A is this. You know how to compute this. So 100 is divisible by 5, and the first number greater than 0 divisible by 5 is 5. We divide it by 5 as we want to find all numbers divisible by 5. We divide it by 5 and we add plus 1. We add 1. So we have 1/2. Similarly, we get this. So first positive integer divisible by 7 is 7, okay? And the last integer divisible by 7 less than 100 is 98. So we write the same formula for 7 and get 7/50. Now what's this? It's we want both A and B to happen. So it means numbers divisible by both 5 and 7. So there are only two such numbers. So we have 1/50. Okay. So in the denominator we have 100 because we have 100 many numbers to select. Okay. So what's the probability of this union? It's this. So we write 1/2 plus 7/50 minus 1/50. So we get this. Now we consider a family with 4 children. Okay. E denote the event that this family has children of both sexes, and F denote they have only one boy. At most one boy. Okay, we will decide if these two events are independent or not. Remember, they are independent if and only if we have this equality. So we will compute these probabilities and we'll check if we have this equality or not. Now, what's P of E? It's the event that the family has children of both sexes. So what's its opposite? It's to have only one sex. To have children only one sex. So either they will have 4 kids, which 4 girls, okay, or 4 boys. So if we have, for example, if the family has only 4 girls, so it's the probability of that is 1/2 to the 4. But they may have 4 boys too, so we multiply it by 2. Now, this is the case where they have children of same sex, okay? Now, the opposite of this is the complement, you may say, is 1 minus this, so we get 7/8. And for F, the event that they have at most one boy. Now, either they will have no boys, right, or one boy. So if no boys means they have all girls, four girls, or many girls. 4 girls, so we have this, okay, this probability. And the other case, this is one case and this is another case. So this is the case where they have a boy and 3 girls. So to get a boy is 1/2. To have 3 girls, right? They have 4 men children. 3 girls, the probability is this. Why do we multiply by 4? Because we don't know which one is boy, right? Maybe their first child is boy or second is boy. So we multiply it by 4. Thus we get this result. What's E intersection F? They need to have children of both sexes and at most 1 boy. So the case is this, okay? Either the first one will be boy and the remaining ones will be girls. Either this or. Okay, we have 4 such events. So 4/2 because for example, first child may be both boy or not both, maybe both, but not in this case, either a boy or a girl. So we have 2 options for the first one and for the second one again. So we have 2⁴, okay? Thus, this is the probability. Now we have this probability. We will check this equality. So on the left, we have 1/4 as we computed before, and on the left, we multiply these probabilities. And it's obvious that they are not equal. So the events that are given are not independent. Okay. So the case where they have 5 children is homework. Now, okay, so we will find a solution for this recurrence relation with these initial values. So we will first write characteristic equation. Remember, we will write, for example, for a sub n minus 3, we will see that as r to the 0. So for this, it's r, for that r to the r squared, and for this, it's r to the 3, r cubed. So we get this one, okay? And as we have an equation, a polynomial of degree 3, we need to find a root of this equation manually, okay? So you may try 0, 1, -1, 2, okay? First you try that. And we see 1 is a root of this equation. So a factor of this polynomial will be r minus 1. So let's divide this one by this r minus 1 by polynomial division. So what do we have? Of course, the remaining part will be 0 because this is a factor of this equation. So we may rewrite this given polynomial as in this form. I'm r minus 1 times this, okay? So r squared minus r minus 6 can be written as in this form, r minus 3 times r plus 2. Then we know that all roots of this polynomial, which are 1, 3, minus 2. What do we do now? We rewrite this recurrence using these roots as in this form. Now, using these initial values, we will find alpha 1, alpha 2, and alpha 3. So first we put n equals to 0, we get this. Okay, when n equals to 0, we have this equality. When n equals to 1, we have this, and 2, we have this. You know how to solve this equation system. Okay, you need to know. So we get these multiples. Thus, now we plug them into this equality. And we have this. Okay, this is the last question. So we will consider the non-homogeneous linear recurrence relation. Okay. Now, first one says that try this to see it's a solution. Okay, so when n minus 1, we have n minus 1. We plug here n minus 1, we get minus 2, n minus 1 plus 1, we get n there, okay? Then we plug this into this equality and get, here we have 3a sub n minus, we don't have the equality now. We need to show it. We need to show this satisfies this equality, satisfy that equality. So on the right, from right we start, okay? So we have 3a sub n minus 1 plus 2 to the n. We have this one. So instead of a sub n minus 1, we write this and get that. So we have this and this. And it can be written as in this form, okay? And what's this? It's a sub n, right? It's given already. So on the left, we have this. On the right, we have an, okay? So we show the equality. It means this is the solution. A solution, sorry. And it is non-homogeneous part of the recurrence relation. Remark that also. Now we will find the homogeneous part. So we write the characteristic equation, okay, of this, and then we have, as r equals to 3, we have this. Now this is the homogeneous part. Now we know from A that this is non-homogeneous part. Then we get this recurrence relation. This is the general solution. Now we need to, okay, this may be alpha or this may be alpha 1. They are the same, okay? Sorry about it. So in the last part of the question says, when you have this initial value, find the solution. So we plug n equals to 0 in here, in this equation, and get this, okay? So we get alpha, the value of alpha, and hence we obtain this. Okay, this is the solution when we have a0 equals to 1. So this was the last question. If you have any question, you may write an email, or yeah, that's it, because this week is the last week of the courses. So good luck with the exam. See you.